Consider the integral of x over 1 plus x squared from negative infinity to positive infinity. Let's try computing it the Riemann way, using the so-called improper integrals. What is this about? Integrate from negative r to positive r. As r goes to infinity, the answer is 0. This seems plausible. It's an odd function, and the positive and the negative areas perfectly cancel. But wait, what if we use a different exhaustion? Integrate from negative r to 2r. Now we're including more of the positive side. As r goes to infinity, the answer is now the natural logarithm of 2. Same integral, but two different answers. This is the problem. Riemann improper integrals can depend on how you exhaust the domain. Different exhaustions can give different values. Quick recap. In video 1, we defined the integral as the limit of averages over uniformly distributed sequences. Sequences that visit every region in proportion to its volume. In video 2, we saw the brittleness of Riemann when faced with non-continuous functions, and how Lebesgue fixes this using a specific generator and the notion of negligible sets. We'll build on both. Links in the description if you need a refresher. But at least on bounded domains, Riemann gives you one answer, a number or not integrable. We have the formula, the integral equals the volume times the limit of the average. For infinite domains, Riemann uses improper integrals, limits of integrals over finite regions. But here's the problem. The limit can depend on the exhaustion order. In our example, symmetric gives 0 and negative r to 2r gives the natural logarithm of 2. To properly integrate on the d-dimensional real space, we need a different approach. We saw that uniformly distributed sequences are the foundation for integration on bounded domains. Here's the key insight. Instead of letting integration bounds go up to infinity, we transform our points to cover more space and compensate for that transformation. But first, we need to understand the bounded case. So let's build the tools. Consider a linear map L from d-dimensional real space to itself. Here's a fundamental observation. For any box Q with non-zero volume, the volume of L of Q equals some constant C times the volume of Q. This constant C is independent of which box you choose. We call this constant the absolute determinant of L. Look at the two different boxes Q1 and Q2. Both get transformed by the same linear map. The ratio of image volume to original volume is the same for both. That's the absolute determinant of L. But there's more to the determinant than just volume scaling. Consider a rotation. The corners move, but the orientation stays the same. The sign determinant is positive. Now consider a reflection, a linear map that flips the plane. The corners swap and the orientation reverses. The sign determinant is negative. The sign determinant captures orientation. This distinction will become important when we compare Riemann and Lebesgue integration. Now for smooth maps that aren't linear. At any point, we can approximate the map by its best linear approximation, the Jacobian. For a differential map T at point x0, the linearization is T of x0 plus delta x equals T of x0 plus the Jacobian applied to delta x plus an error term. The little o means this error shrinks faster than delta x itself. It becomes negligible as we zoom in. Watch the tangent plane follow the point as it moves across the surface. The Jacobian captures the local linear behavior. We've seen the Jacobian describes how functions behave locally. But what happens to uniformly distributed sequences under such a transformation? Watch. A uniformly distributed sequence in Q. Apply a smooth map T. the sequence is no longer uniformly distributed. The points bunch up in some regions. To integrate correctly after transformation, we need to compensate for this non-uniformity. We need weights. And those weights are what we'll later call density. But a sequence is just countably many discrete points. How can we define density for something discrete? By averaging over many points, then shrinking neighborhoods. From the discrete sequence, we extract a continuous density function. Let's make this precise. Take a uniformly distributed sequence in a box Q. For any subbox B, the fraction of points in B approaches the volume of B over the volume of Q, as we include more and more terms. Here's the key insight. We can define a density at any spatial location x0, not at sequence elements, but at every point in space. First, fix a neighborhood B around x0 and let n go to infinity. This stabilizes the local frequency. It tells us how often the sequence gets close to x0. Then shrink B toward x0. The limiting value is the density at that location. Watch. The volume of B cancels, and the limit of a constant is just the constant. For a uniformly distributed sequence in Q, this density is constant everywhere, 1 over the volume of Q. The density emerges at every spatial point, even though almost no point is ever actually visited by the sequence. It measures how concentrated the sequence becomes near each location, not whether it ever hits that exact point. Now, what happens to density under a transformation? Start with a uniformly distributed sequence in Q. Apply a smooth invertible map T. The image points are not uniformly distributed in T of Q. So fix a point x0 in Q with image y0 equals to T of x0. What's the density at y0? We take the same limit, shrink a box around y0 in the image space, and compute the density there. First step, counting points in by is the same as counting xk in T inverse of by. By uniformity, this fraction approaches volume of T inverse of by over volume of Q. Second step, as the box shrinks to 0, the function is fully described by its Jacobian. The linear approximation becomes exact in the limit. The ratio volume of T inverse of by over volume of by approaches the absolute determinant of T inverse, which equals 1 over the absolute determinant of T. So the density at y0 equals 1 over volume of Q times 1 over the absolute determinant of the Jacobian, evaluated at x0, which is T inverse of y0. Let's connect what we've learned. Recall from video 1, the indicator trick. The integral over d equals the integral over a surrounding box Q of f times the indicator of d. Any bounded domain D fits inside some box Q, so bounded integrals are well defined. And from video 2, irrational rotation gives us a uniformly distributed sequence for any box Q. The limit of the averages converges for all starting points except a negligible set. But for the d-dimensional real space, there is no enclosing box, and letting the bounds go to infinity is just exhaustion, unreliable as we saw for Riemann. We need an alternative approach. Here's the alternative. Start with a box Q and a transformation T. We can first generate a uniformly distributed sequence in Q using irrational rotation. Second, push the points through T to get points in T of Q. These are not uniform in general. They bunch up where T compresses. Third, compensate with density weighting. Now the averages converge. Remember, For uniformly distributed sequences, the constant density 1 over volume q cancelled when we multiplied by volume q. Now the density is spatially dependent, so we need a spatially dependent weight, volume of q times the absolute determinant of the Jacobian at each point. So let's derive the formula. To integrate g over t of q, naively averaging g of yk fails. The points are bunched, not uniform. The correct approach weights by the absolute Jacobian determinant. We define the integral of g over t of q equals the integral over q of g of t of x times the absolute value of the Jacobian determinant of t at x. This is the change of variables formula for the Lebesgue integration, valid for all integrable g and smooth invertible t. Why does t need to be invertible? The weight involves t inverse, and invertibility means the Jacobian is non-zero, so the weights stay finite and the cancellation is well defined. Plus, every region of t of q can be reached by points from q. Now we can tackle infinite domains. The key idea: map the unit cube smoothly onto all of the d-dimensional real space. We need a diffeomorphism, a smooth invertible map with smooth inverse. Example, the logistic map. Phi of x equals e to the x over 1 plus e to the x. Is this a diffeomorphism? Let's check. It's smooth, strictly increasing, so it's a bijection from R to the interval 0 to 1. And it has a smooth inverse. Yes, it's a diffeomorphism. Watch how the real line collapses onto the interval 0 to 1. Points from far left and far right are all mapped into this bounded interval. Now extend to higher dimensions. Apply the logistic component-wise. Capital phi of x1 through xd equals phi of x1 through phi of xd. This defines a diffeomorphism from the d-dimensional real space to the open unit cube. And the inverse goes the other way, from the unit cube to all of the d-dimensional real space. Now we can define Lebesgue integration on all of d-dimensional real space. Here's the definition. The integral over d-dimensional real space of f equals the integral over the unit cube of f composed with capital phi times the absolute Jacobian determinant. The right side is an integral over a bounded domain, so we know how to compute that. No exhaustion needed, the integral is defined directly. And here's the key theorem. For any diffeomorphism capital phi from the unit cube to the d-dimensional real space, the definition gives the same value. It's well defined. Let's apply this. Recall, the logistic map phi of x equals e to the x over 1 plus e to the x. The Jacobian, or in one dimension just the derivative, is e to the x over 1 plus e to the x squared. Look at the area under this curve. It's exactly 1. Here's the change of variables formula. The integral over r of f equals the integral from 0 to 1 of f of phi inverse times the inverse absolute derivative. Now apply it. We want to integrate e to the x over 1 plus e to the x squared. Notice, the integrand is exactly the derivative of the logistic. So when we apply the change of variables, the derivative times its inverse cancels to 1. The integral over the real numbers equals the integral from 0 to 1 of 1. That's just 1. Let's return to our example. The integral of x over 1 plus x squared over the entire real line. Riemann gives different answers for different exhaustions. Symmetric, negative r to r gives 0. Asymmetric, negative r to 2r gives the natural logarithm of 2. Different answers for the same integral. With Lebesgue integration, this function is not integrable. But that is a clear, unique answer, no ambiguity. In general, a finite Lebesgue integral means all exhaustions coincide. An infinite or undefined Lebesgue integral means exhaustion pathologies are possible. But can we fix Riemann with change of variables? No. Riemann integration is not stable under change of variables. A function can be Riemann integrable on the unit interval, but after applying a diffeomorphism, the result might not be Riemann integrable. Lebesgue integration is stable under change of variables. That's what makes the definition work. A quick side note on orientation. How does our understanding of change of variables help here? Riemann integration is orientation aware. The direction of integration matters. In physics, for example, think of work done along a path. Reversing direction flips the sign. We can express this in our uniformly distributed sequence framework. Q is a box, and L is a linear map that encodes the orientation, either rotation or reflection. When we apply a linear map L to our box Q, the integral over L of Q of f equals the determinant of L times the integral of Q of f composed with L. The determinant of L equals +1 for rotation and -1 for reflection. The key insight: by using the sign determinant instead of the absolute value, we can make our sequence-based framework orientation aware. Let's summarize with two key conclusions. First conclusion: bounded domains, no improper integrals. Here, Riemann integrable functions are a subset of Lebesgue integrable functions. Second conclusion: integration over bounded or unbounded regions. Lebesgue always gives a unique answer. Riemann with improper integrals can give different answers depending on the exhaustion. In this case, Riemann is not a subset of Lebesgue. Coming up next, the fundamental theorem of calculus. It doesn't hold in general for Riemann or Lebesgue. We'll explore when it fails and what that tells us about the nature of integration. Thanks for watching. Subscribe for more.